Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to lecture number 19 on the subject of computer organization and assembly language programming. The title of today's session is Hack Assembly Programming Part 1. Before I start today's session, I believe that if you are not clear about the two hack assembly instructions, the A instruction and the C instruction, then this lecture might not make much sense to you. I strongly recommend that you should go through the lecture number 16 and 17 first and then fall back to this. Anyways, today we will start with a quick recap of the two hack assembly instructions. Then using those instructions we will write some very basic but meaningful programs in the hack assembly language. Since we have yet not written an assembler for the hack assembly language, so we'll make use of the CPU emulator, in which we will load, run and debug our assembly programs written for our hack computer. We will write and understand a Hello World hack assembly program today. Then we will download the hack CPU emulator, install it on our system and see a demo of executing the Hello World hack assembly program on the emulator. And finally we will see and understand a problem related to program termination and devise a solution for it. My dear students, in the later sessions we will see other related concepts of built-in symbols, labels, variables, branching, iterations, pointers and handling of the I/O devices. These all are related to the hack assembly programming. So we have a lot to do today, so let's start playing. Well, before proceeding, I will like to give you all a quick recap of the hack assembly instructions, as I have just said, which may serve as a bit of mind dusting for you all. Well, before the instructions, let us talk about the registers. Yes. And the two types of memories as well, which are available in our hack computer. So in our hack computer there are three registers. First of all, the D or the data register. As the name implies, this is used to hold data, a data value. The second one is the A register. A for address, and this can be used to hold the address as well as the data. If it is the address, then that address might be of some data item inside the RAM, or might be the address of some instruction inside the ROM. The third register is the M register or the memory register, which represent the currently selected RAM register. We will be using this M register whenever we will be reading or writing the data memory or the RAM. Let me say something about this ROM as well. This is of course the read-only memory, but somehow we will be able to load our machine or assembly programs in it. Okay, now let's have a recap of the two hack assembly instructions. You can see the syntax of A instruction at value, where value is the unsigned constant and can have values ranging from 0 to 32767, being 15-bit. This value can be a data value or can be the address of the data memory, RAM, or the instruction memory, ROM. This is the complete syntax of the C instruction. It can be used in two ways. We can either store the result of the computation, and the computation can be one out of these 28 inside some destination, and destination can be one out of these 7. Maybe if you include null, this is also 8. So this one of the syntax of the C instruction is destination is equal to computation, or maybe based on the result of the computation, the programmer can decide if he or she wants to jump to some other address in the ROM, in which case the destination and is equal to sign over here are omitted, and we have a jump directive over here, and it can be unconditional jump as well as the conditional jump. And we all have seen this in detail in the previous lectures. Let me show you some examples as well. Well, if you want to assign an integer constant 10 to D register, like this, there is no single instruction that can do this task. So first we place an integer constant inside the A register using this A instruction, and then assign it to the D register. In this example, you can see the A register is used as a data register. However, if a programmer wants to increment D register, this can of course be done by a single C instruction. And if you want to write an integer constant, let's go 65 at RAM address 23, these are the two instructions that will do the job. Similarly, these two instructions are reading the RAM contents at address 17 and placing them in the D register. And these two instructions are writing the contents of D register inside RAM at address 17. Note that in these three examples, A register is used as the address register. Well, this example over here writes an integer constant 10 at RAM address 17. Note that over here in the first two instructions, the A register is used as a data register, and in the next two instructions, the A register is used as a address register. And this example, read the contents of RAM location 3 and write those contents at RAM location or address 5. And finally, this is an example of an unconditional jump, and this is an example of a conditional jump. Note that in these two examples, the A register points to the address of ROM, that is the instruction memory. So my dear students, this was a quick recap of the previous lecture, and let me move ahead. I think I have spent enough time again to revise the use of A and C instruction. Now it is time to review the Hello World assembly program of our hack computer. Okay. Well, this program will not, of course, display a traditional Hello World message on the screen. Rather, will simply add two constant numbers, 27 and 13, and write the result at address 0 inside our RAM. So this is what this code is doing. So this hack assembly program has just 6 instructions, 0, 1, 2, 3, 4 and 5. The first two instructions are placing constant 27 inside the D register. First we are placing it inside the A register, and then we are using the C instruction to place it inside the D register. The instruction address 2 at 13 is placing a constant 13 inside the A register. Then the instruction at address 3 is a C instruction that actually performs the computation and places the result inside the D register. So now we have the sum of these two constants, 27 and 13, inside the D register. Finally, these two last instructions are writing the computed value inside RAM at address 0. So dear students, we are done with writing of our first assembly program that adds two constant numbers, 27 and 13. You can do this using any text editor, and then saving the hack assembly program in a file. Suppose I have saved it in addv0.asm. Next, we need to load this program inside the read-only memory or the instruction memory. You can note that the 6 assembly instructions over here are loaded inside the ROM from addresses 0 to 5. But the hack computer will not be able to execute these symbolic instructions as it do not understand them, because this is a symbolic view which is shown to you over here. So there is one more step that we need to perform after we have written the assembly program. And that step is translating this hack assembly program into hack machine code, that is language of zeros and ones. This can be done manually as I have done for you, and I think you can also do that if you have taken the lecture number 17 of this course. Uh, you can see that the instruction at address 0 is at 27. This is an A instruction. So over here you can see the most significant bit is 0, showing that this is a A instruction, and the remaining 15 bits actually contains the constant 27. Similarly, this is a C instruction, and you can see over here this is a 1 in the most significant bit, showing that this is a C instruction. And then we know that uh, there are 3 bits for the destination, 3 bits for the jump, 2 bits are reserved, and probably the 7 bits are there for the destination. My dear students, please do try to translate these 6 assembly instructions to this machine code, corresponding machine code. This practice will help you all when we will be writing our own hack assembler uh, uh, in C in the later part of this course, inshallah. Okay, well, this slide shows another version, an improved version of the same program. You can note this is add v1.asm. In this program, we are adding the contents of RAM address 0 and RAM address 1 and writing the result at RAM address 2. So we are not just adding two constant numbers, 27 and 13 this time. And it is assumed that before starting this program, the user has placed two values of his own choice at RAM address 0 and RAM address 1. I hope this code is quite self-explanatory, and this is the machine code. Let me move ahead. Okay, now $100 question is how we are going to execute this hack assembly program translated to this hack machine language inside the hack computer. Well, dear students, computers don't understand the symbols other than 0 and 1, as I have already said. And therefore, before we can execute anything which is written in the symbolic hack machine language, we have to first translate it into the binary code, and this is done by a program called assembler. And having produced the target code in binary, we can actually take this file, load it into the hack computer, and finally execute the intended program. We will inshallah write the hack assembler in later part of the course, and for the time being we will use another program for the purpose called the CPU emulator. My dear students, in contrast to a simulator, an emulator attempts to mimic the hardware features of a production environment as well as the software features. Emulation is the process of artificially executing code intended for a foreign architecture by converting it to the assembly or machine language of that CPU. The CPU emulator that we will be using is designed and developed by students of Interdisciplinary Center Herzliya F.E. Razi School of Computer Science, headed by Yaroun Ukraines. I'm sorry uh, for the pronunciation if I have made it wrong. Well, this CPU emulator is a software tool built in Java, and we can load hack assembly programs into this CPU emulator instruction memory, which we have called the ROM. The CPU emulator will translate it into the corresponding machine language and execute it. I'm sure that the CPU emulator has already been downloaded on your system, and this was done probably in the second lecture of this course when you downloaded the tools subdirectory from the course Bitbucket account. If you have not done so, please do that now. The Microsoft users can use the CPU emulator.bat file, while the Linux and Mac users can use the CPU emulator.sh file. The way we did with the hardware simulator, we just need to set the execute permissions of the CPU emulator using this command, and then we need to execute it. So this slide summarizes the process of loading the hack assembly program into the CPU emulator. This is the GUI of the CPU emulator. Uh, Soon I'm going to explain all this GUI to you, and it is a software tool built in Java. And let's move ahead and move on to the terminal and show you a demo of loading and executing the version 1 of our uh, add program in the CPU emulator. So here is the terminal program running. Well, right now I am inside the lecture codes and tools. If I do ls, you can see the other than the hardware simulator.sh, we have the CPU emulator. Where is the CPU emulator? This is a CPU emulator .sh for my Mac machine. Let me set the permissions by using the command chmod plus x, that is set the execute permission to this program. So it is done. Now let me execute it, this CPU emulator.sh program, the C and running now. So this is the GUI of beautiful GUI of the CPU emulator. Great. And before I describe different components of this GUI, let us first load a hack assembly program inside this emulator. So we just click this open icon in the top left corner, which will open the window. And since inside the lectures we are in lecture 19, so let me load this program add v1.asm. Remember, add v0 was a program that added two constant 27 and 13, I think, and add v1 actually adds the contents of RAM location 0 and 1 and places the result in RAM location 2. Okay. So you can observe this is the ROM panel or the instruction memory where the assembly code is visible. You can always change the code to the view to binary. Now this is the binary view of the machine code, and back to the assembly view. Do note that there are no comments, no white spaces, no new lines over here. Okay, remember this, each location is a 16-bit instruction. Right now it is being shown in the assembly, and this highlighted instruction at address 0 shows that this is the next instruction to be executed. Beside this ROM panel, this is the panel showing the RAM, random access memory, or the data memory. Our hack computer has 32K words RAM and each word of 16 bits. And let me scroll down, you can see the addresses and the contents of these locations, which are right now all initialized to 0. Well, dear students, RAM is used for general purpose data storage and of course for the screen memory map and the keyboard memory map. So we have a 32K words RAM, and let me say that we also have the size of this ROM is also 32K words. So there are 32K locations. So we can have 32K instructions in a program that can be loaded inside the ROM. Then the three CPU registers, we have the program counter, the A register and the D registers, which are shown. The program counter is shown below the ROM. Right now its contents are 0, and you can see the instruction at address 0 is highlighted. That is, this is the next instruction to be executed. Over here we have the A register. This is shown below the RAM, and for addressing it is used to either select or enable a specific RAM location for reading or writing, or in case of jump instruction, it is used to set the program counter to a specific ROM address. The D or the data register is also shown over here. And these are the two IO devices. The screen having 256 rows and each row having 512 columns. We have a keyboard that is attached with our physical system keyboard. And finally over here we have the ALU, which can compute various arithmetic and logic functions. You can see the two possible inputs. They can be from the D register and from the M or the A register. And finally the GUI also shows the output of the ALU over here. Okay dear students, now after having an understanding about different GUI components of our CPU emulator, let us execute this program which actually adds the contents of RAM location 0 and RAM location 1 and plays the result at RAM location 2. So let us first write two integers at RAM location 0 and 1. Let me write over here, let's suppose 23, and let me write over here 17. I can write anything of my choice, and after this program will execute, the sum should be 40. So we have two options. One is we can single step through this code, and the other option is we can simply run this code, and this slider can be used to control the speed. Let me set the speed over here and let me run it. So you see now it is computing, and here you go. We have the 40 over here. Let me make another run. Let me use this to reset it to 0. You see the PC has gone to 0. Let me clear the contents of the RAM by pressing this button. The contents are cleared. Let me write minus 23 over here this time, and let me write 10 over here this time, and this time instead of going in one go, let me go step by step. Let me click this first, and you see this at 0 instruction will place a 0 inside the A register. So a 0 has come inside the A register. This instruction will read the memory contents from A and place them in D, that is minus 23 will be placed inside the rate. Now this will place a constant 1 inside the A register. So you see a constant 1 has been placed inside this register. Now this is a computation that will be done by the ALU, that is D plus M. The contents of D are minus 23 and the contents of M are RAM location 10. So over here we'll be having 10. So you see the result is minus 13. Now we are going to place this result inside the RAM again. So the RAM address is 2. So we have placed 2 inside this A register. Now the writing will be done, and the writing will be done at RAM register 2. So you will see minus 13 will come up over here. So that is great. Let me rewind again, and let me clear the RAM again, and let me give it another run. And now let me run it in one go. Well dear students, you can see the instructions are being executed one after another, and we have controlled the speed of the program as well. And finally you can see the result 18 over here at RAM 2. But do note that the program has not halted. Rather it is moving on and on and on, executing these blank or no operation instructions after this last instruction of our program at address 5. So this should not happen. Let me stop this program by clicking this and fall back to slides to solve this problem. The problem of program termination. Well dear students, if you load this program inside the CPU emulator and run it using the fast forward button as we have done just a minute before, the computer continues to execute the program starting from address 0, then 1, 2, 3, 4, 5, and it Do not stop after executing the fifth instruction or the last instruction. It continues executing, moving ahead, executing the no operation instructions. And there is a possibility that there is a malicious code sitting over here placed by a hacker, and after the execution of these no operation instructions, the malicious code run and give the control of your computer to that hacker. So how to avoid this? Well, there is a very simple way that we are using right now to avoid this. We are using a jump instruction. We are placing these two instructions over here. Add 6, 0 semicolon jump. Add 6 will place address 6 inside the A register, and this is an unconditional jump to address 6. Again place 6 in the A register, unconditional jump to address 6, and so on and so forth. So these two instructions are used at the end of every program that we are going to write, and these are known as the program termination instruction. Let me move on to the CPU emulator again to have a quick demo of this concept. So it is running. Let me load the program, this time add v2.asm, and you just note that this program is the same program. Other than that, it has just these two instructions at the end, the program termination instruction. Let me clear the screen, place a value over here 120, and over here 35, and let me set the speed and run it. You will soon see the result over here, and the program will not move below, rather it will get inside this infinite loop and keep running these two instructions. So the problem is solved. Remember, dear students, computers never stand still. They always do something even when you don't even touch the keyboard. So by putting these two instructions over here, I have ensured that this assembly program do not suffer with a vulnerability that can be exploited by a hacker using some flavor of NOP slide attack. Let me stop the execution of this program and fall back to the slides. Okay, so that is it for today's session. My dear students, please do understand and practice what we have done today. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning, and Allah Hafiz.